Hello everybody, my name is Esther. I'm a master's student of the Bioinformatics program at University of São Paulo. This is my final project for the course Seminars on Advanced Topics in Bioinformatics. I'll be discussing anomaly detection. This presentation is based on the course named Machine Learning taught by Stanford teacher Professor Andrew, and it's made available by Coursera. The authorship will be pointed for each image that I show. Anomaly detection is a branch of the machine learning field. So let me define or talk a little bit about the machine learning. Arthur Samuel in 1959 said that machine learning is the field of study that gives computer the ability to learn without being explicitly programmed. Tom Mitchell in 1998 said that a computer program is said to learn from experience E with respect to some task T and some performance measure P if its performance on T, as measured by P, improves with experience. So here we have a more hands-on definition that implies that the computer will be doing something for some time, and you have to be able to measure the performance that it is its performance in doing that task. So keep in mind that whatever we do here, we must have a way to measure if things are going correctly or if things are going wrong. So, okay. Now, for anomaly detection, first let us discuss what is really an anomaly. So Hawkins in the 1980 said that an anomaly is an observation that deviates so much from other observations as to arouse suspicion that it was generated by a different mechanism. Barnett and Lewis in 1994 said that an outlying observation or outlier, or really an anomaly, is one that appears to deviate markedly from other members of the sample in which it occurs. The challenge is to identify data, which could be an observation or an instance or an event. Those are names we could use for it. So identify data as anomalous, setting it apart from those said to be normal in a given context. Here the context is really the key. Let me give you some examples of what applications that there may be for anomaly detection. So let's say we have several X-ray images from lungs and we would like to tell if it's a normal lung or if there is a sign of alteration, which could be a tumor or pneumonia. And another example is bank daily transactions from a given client. We want to know when there's a normal behavior compared to the client history, or if there's something strange, suggestive of robbery or fraud in process. So we could have data about what time he usually buys stuff, or the location, or really the the price of things he usually buy, and we want to know if there's maybe something strange. And another example is, suppose we have a computer network warehouse where We collect data about CPU load and memory usage and data traffic, and we want to know if everything's okay, if everything is following a normal pattern, or if there's an unusual pattern like a malicious activity or a hardware problem or an internal error that is clogging the flow or something. So we want to be able to detect those things. So it may be implicit, but I want to make it explicit that anomalies, they come in all shapes and sizes, and there's no defined behavior. That's why they are anomalies. So we don't want, there are many ways in which something could be anomalous, but and we don't know which ways exactly, but we know the normal behavior. So knowing what is normal, we'll be able to tell if there is something strange, even though we don't know beforehand what could be this strangeness, or the source, or what is strange really. And it's usually something you wanna flag to look further on, and you really wanna detect something that's strange, and you usually will want to give it a closer look. There are several techniques that could be applied to detect an anomaly. They could be based on density, they could be based on distance metrics, and they could be uh, based on classification algorithms, for example, supervised learning algorithms, or maybe they could be based on statistics, and that's what we'll be focusing on this video. The statistics method is based on the Gaussian distribution, and it the variables which will look could be discrete, natural numbers 0, 1, 2, 3, or they could be continuous variables like 1, 1.5 and square root of 2 or pi or whatever. And we assume beforehand that the majority of the data is normal, and we'll be having a few anomalies in our data set. And it could be treated as a semi-supervised learning algorithm, because we it's possible to implement without knowing what are the anomalies and what are the normal data, but usually but it will also work when you know that beforehand. So I'll give you a more detailed example to be able to explain the Gaussian distribution and how this works. So let's say we are manufacturers of airplane engines, and we have data about these engines temperature and vibration, and we have a set of observations or events, and they will be named x1 and 2 and all until m, which is the size of our sample. And we want to be able to know if a new sample, after we observed a lot of different engines, we want to know if this brand new engine it's good to go, or if it is probably there's something wrong with it. So the new engine, every new example can be called X. So let's say we plot this data. This is our observations, each x here is a new agent, and this is the heat, and this is the vibration that it produced, that we tested after it was done. And these these are all normal agents, and we want to be able to tell if, well, this agent had this temperature and this vibration, it looks like all the others, so it is probably okay. Or if we see a new agent and it has a temperature that is higher than the majority, and also vibrates much less than the others, we wanna flag it as an anomaly and look further if there is something wrong with that. So this is the Gaussian distribution. It is also called the normal distribution, and it's often referred to as the bell-shaped curve because of its shape. And the normal distribution has its parameterized. The parameters that define it are the mean, which is the average, and it's denoted by the letter mu, and it's really the mean, and the variance, which is sigma squared, which we could also write that statement as x is distributed as a normal distribution parameterized by mu, which is the mean, and the variance. And the Gaussian, so for a given x, if we have if we define a given mu and a given variance, and we vary the value of x, we will end up, and we apply this formula, we will end up with this curve. The Gaussian distribution curve, as I said, has the parameters mean and variance. These are examples of normal distribution, and in red we can see the standard normal curve, which has mean 0 and and the variance equals to 1. Well, the variance will tell us where is the center of this symmetric distribution, whereas the variance will tell us the width of this curve. So let's take the blue curve. Here we have a smaller variance, and we can see that the shape gets really thinner and with a higher peak. And if we pick a larger value for the variance, we'll see that the curve gets really flattened and with a much lower peak. If we shift the mean, what we will see is that the center will shift with it. If we pick a negative number for it, like the green curve, we'll see that the mean will be the peak and the curve will be dislocated to the left, and if we pick a positive value, we'll see a curve over here at the right side. As a property of the probability distribution curve, the area under each one of these curves is equal to 1, and that is interesting because there will never be something with a probability higher than 1. or 100%. Okay, so let's say we have several observations of a given variable, for example, the temperature variable. We collect a lot of data and we want to be able to use it. So, how do we calculate the mean? Well, is with some odd values we observed and divided by the number of observations. Then we use this mean over here to uh, calculate the variance. So the variance will be the sum of all the difference between our observation minus the, well, it's the difference between the observation and the mean, and this is squared so that the values will be always positive. And then we divide everything that we sum by the number of observations. And sometimes we may see this formula differently with m minus 1, which will give different mathematical properties, but for the machine learning field it really doesn't matter which one you use. It's more common to use over m, or I mean divide by m, but it's possible to see it divided by m minus 1, and this is they are both okay. There's no right or wrong, just this one is more common. Okay, so we calculate the probability, I mean the parameters of all of our of one of our variables. Then we do it for all of our of the variables. I mean, if in the data warehouse example, x1 could be the CPU load, and x2 could be memory usage, and x3 could be the data flow. I mean, we calculate the mean and the variance for all of our variables we want to be able to use and to predict the probability of a given x to occur. So how do we do that? We simply, for this given x, we multiply the probability of this x happening for one variable, and then multiply it by the other variable and the other observation you made, and so on until you for all of your variables. And this will give you the probability. This will be the product of these probabilities, different probabilities, and you will be able to tell the probability of this given x occurring. So let me give you a more visual explanation. So take the aircraft engine example, or some other example. Let's suppose we have an x1 variable, and it has this. We calculate the mean and the variance, and this is the shape of the curve for this variable. We have for this variable we have this shape of this curve, and for the second uh, variable, we will have a different curve, and this is the shape of it, so they're different curves. And if we plot the probability, no, if we plot the values of x1 and the values of x2, where they encounter, they will have a certain probability. So uh, this represents the probability, and this is the observation that you could make with for that variable, and these are the values that could be found for this other variable. So notice here, we can notice here that in the middle we have a higher probability of this happening. Okay, so that's exactly what we wanna know. If given a given observation, it has a high probability of happening, or if it's very low and then it's not common, it's not normal, so it's an anomaly. So everything that lies here on the deep blue, and it would be, we want to flag it as anomalous. So how do we do that in practice? I mean, if we were to see some, let's say we have some two new observations, and we want to know if they are normal or anomalous. So the first thing would be calculate, to define an epsilon, and let's say we define it as 0.02. So we wanna see, we wanna flag as anomalous something that has a chance lower than 2% of happening. So we calculate for the first dot, we take its value here, it's 4, and we calculate its probability, given the probability of it happenings for the value of, I don't know, 4-ish, and the probability of it happening if its value is 4 again. So, and we multiply those probabilities, and we will have a value of 0.04, which is much higher than our epsilon, so we would flag it as a normal value. On the other hand, if we calculate here, we see almost 8 and 0, so we calculate the probability of seeing an 8 here. Here you can see that it's lower in this curve here, and of seeing a 0 in this other distribution. Okay, here is the 0, so we see here that 0 is very unlikely to happen, and if we multiply these probabilities, which is the area under the curve here, and we'll come up with this value, which is 10 times smaller than the defined epsilon, the epsilon that we chose. So we would flag this as an anomaly. Okay, let us put this in more formal terms. What would we want to do to flag an anomaly? First, we would choose features that we thought that might be indicative of anomalous examples. and we would fit parameters. We would uh, calculate the mean and the variance for each of these samples, and giving a new example, we would calculate the product. This pi symbol here is really the product of all our observations. And so we would go from our first uh, feature, our first variable, and go and we would calculate its probability and then multiply by the second and the third and the nth probability, and we would have the probability of this new example being happening. So if then we define an epsilon, and if the probability is smaller than the epsilon we define, then we would flag it as an anomaly. So how do we implement this algorithm in practice? Well, first we'll collect data about all features for each sample of our data set. Then we will divide our data set into three subsets. The first is the training set that we will use to fit the model P of x. This is the source from which we will get the mean and the variance for each feature to apply the formulas shown in the previous slide. After we fit our model, we use the second subset, the cross-validation set, as a source of data to feed to our model. So for each x, we want to predict the outcome, if this given x is an anomaly or is the normal data according to epsilon. And because we know previously which is the correct answer for this x. I mean, we know which x has a y equals to 1. I mean, we know if it is an anomaly, and we know if y is 0. So that gives us a tool to evaluate our performance. As I said in the beginning, machine learning implies that we must have a way to evaluate how our algorithm is doing. So, and here's is where we can do that. So we can adjust epsilon, we can choose maybe different features, and finally we can use it, you can test it using our test set. So after tuning the parameters with the cross-validation set and choosing the appropriate epsilon, we can now present to our model new data, which is the test set, and we want to see if it evaluates correctly all these sample. Why we do that? Well, if the training set has some skewed values, I mean, if we accidentally choose samples that are not good representatives of the whole data, and we cross-validate it with a skewed set also, with a cross-validation set with some problems. We want to be able to present new data to our model and see if it evaluates correctly if there is an anomaly or not. So I don't think I was explicit before, but I'm saying that we know when there is an anomaly or when it's normal, but if we don't have labeled data, we can assume that all data is normal, and we can evaluate how well it's performing, uh, although the label is not, the data is not labeled. So let's discuss now how we would distribute our data into those three subsets I talked about. Let's assume we have labeled data, which means that for a given x, we know if y is equal to 0, which would mean that the sample is normal, and uh, for a given x, we also know if y is equal to 1, which would mean that we have that is an anomalous sample. So for the training set, which we'll use to fit the model of the probability of it being not anomalous, we want to have only normal data with y equals to 1. So we take our whole sample and we assign randomly 60% of it for the training set, and the rest we divide between the cross validation set and the test set. So for the cross validation set, we'll have 20% of normal data with y equals to 0, and because here we want to evaluate how well we are performing, we must have anomalous data here. So we take 50% of our anomalous data and randomly divide into the cross-validation set and the test set. So how can we tell that our program is performing uh, well? So there are several metrics for that, and I'll be discussing the F1 score. It takes into consideration precision and recall. And precision takes into consideration true positives and false positives. On the other hand, the recall takes into consideration true positives and false negatives. And what does that mean? Well, true positives are samples that were classified as anomalous and were really anomalous, so that they were classified correctly. And the false positive were samples that were classified as anomalous while they were normal. And that tells us the precision of our uh, algorithm. The recall take, counts the true positives that we already discussed and the false negatives, which are samples that were classified as normal and were really normal, so they were classified correctly. So the F1 score reached its best value at 1 and the worst score at 0. So when we are evaluating our program, we want to have F1 score as high as possible. So let's say we evaluate some features and we get an F1 score of 0.8, and we then try and change a feature, we add a new feature, and this score increases. Oh, wow, that's good. You want to keep that alteration. On the other hand, you could also have different epsilons that we want to test and see if they affect the F1 score. Now let's consider a different kind of problem. Let's say we have this data warehouse data, and we collected data from memory usage and CPU load for several machines, and we plotted and we came up with this. And let's say now that we see a new case, a new machine, where we see a high memory use and a rather low CPU load. Now, intuitively, we would say that this is an anomaly because all of our data is within this area, and this one is further out. But in our original Gaussian distribution model, that wouldn't happen because it because we draw imaginary circles with our probabilities, with this being the higher probability area and the probability going decreasing as we go further away from the center, and because of that, we we would predict that this is a normal sample and this is an anomalous sample. But what we would really like to see was something more like that. We would like to uh, be able to have a different shape here to be able to predict this as an anomaly and this as a normal data, normal, yeah, normal non-anomalous data. So how do we do that? With the Gaussian multivariate distribution. Now here are the formulas. We we have the median, mid. I'm sorry. We have the mean, but now it is not a single value that we calculate for each sample. We now have it as a vector of n length, and we use it as a vector. N is the number of features that we'll collect data about. And now the variance gets a little more different. Instead of having one variable, we have a matrix that corresponds to the correlation matrix with length n by n, and we use the vector with the mean here to calculate the variance and the correlation matrix here. And the formula to calculate the p of x, now instead of calculating each probability, we do it all at once with this formula where this is a vector and this is a matrix, and this is our new data that we want to classify as anomalous or non or normal. So this is the shape of a distribution that looks like looks exactly like the ones we saw before with the original Gaussian distribution. As we can see here is x1, which is a feature, and this is another feature, and the if we plot it, the height over here is the probability of it being normal. And as we can see, if we have equal values here for this for sigma, which is the now it's not a variable, it's a matrix, and if we have this inside diagonal with equal values, we're simply getting a higher peak or getting a more flattened shaped distribution. And over here we have it looking from the top down, and that is what we would have. A lower value here represents a higher peak here, and this is no news, right? Now, if we have different values for the variances of each feature, now we can see that if x1 is smaller, we have a smaller width here, and if x2 has a higher variance here, we can see that it goes further. It has a longer axis here. We can see that, and the opposite is also true. If we have a larger value here for x1, we can see that it gets more flattened in this way, and if and as x2 is is lower, then is a smaller value, we can see that this uh, grows smaller as well. Now this is exactly the opposite of what we saw before. Instead of 0.6 and 1, we have 1 and 0.6, and this alters the shape. Yeah, so this is pretty intuitive. Now this outside we call the off diagonals, the outside diagonal. This represents the correlation between these two samples, and as we can see, if we have a positive value over here, we see a different curve with a different shape, and now we get closer to what we were looking for before. We have now a distribution that is let's say more diagonal for our probabilities, and this is as as it as the samples are more correlated, we can see that this gets more well, more concentrated. We have samples that are less scattered, and we can see the values get more, they get closer. And if we have negative values, we can see that it's the complete opposite. The diagonal is now this way, with going from growing smaller from the left to the right. But again, this is exactly the opposite of this one in terms of the correlation. So when we use the multivariate distribution, we are also taking into account how correlated the sample is. And when we use the original Gaussian distribution, we assume that they are independent. So let us compare the two Gaussian distribution models that we saw in this video. Now, for the original distribution, we calculate each probability, and then we multiply everything. And for the multivariate Gaussian, we compute everything at once, with this as a vector and this as a correlation matrix. For as I told you before, this model, the multivariate Gaussian, is able to capture the correlation between features automatically, whereas the original distribution model needs if you want to capture unusual combination of original features, you have to create a new feature. Let's say put x1 divided by x2, and then you have one value that when plotted it won't be, it will go model well with the concentric circles instead of the ellipse shape that we saw over with the multivariate Gaussian distribution. The original distribution is computationally cheaper and deals well with larger n, and because of this calculation as vectors, and we multiply everything from of this matrix, and we have to calculate the inverse of this matrix. This is computationally more expensive. So if we have a large number of features that we are collecting from our data, we'll have to consider this computational cost. And the original distribution works well with a small training set. So if we have small values of m, it will perform okay, but it will still perform okay. But in the multivariate Gaussian, we must have a very large m in order to have a good model, and this could be as high. This proportion has to be, let's say, 10. M must be 10 times greater than n in order to have a good model. Let's now compare anomaly detection and supervised learning. When you have a small number of positive examples, by that I mean examples with y equals to 1, and you have thousands of negative examples with y equals to 0, and maybe a few up to 20 positive examples, and you want to know which is the anomaly. In this case, anomaly detection is preferred to instead of supervised learning, and because supervised learning deals better with large numbers of positive and negative examples, so the proportion is it's more balanced. And as I said before, anomalies come in all shapes and sizes, and it's hard to predict it. So a future anomaly may look completely different from the ones you already saw. So it's difficult for a supervised learning algorithm to learn what it's gonna be an anomaly or not. So in that case, anomaly detection is the way to go. But when you have a large quantity of data that is positive, and you can get a sense of what a future positive example will look like, then you'll be better off with the supervised learning algorithm. So that's what I wanted to discuss in this video. I talked about anomaly detection, which is a branch of the machine learning field that is very interesting. I want you to feel free to comment and make suggestions and corrections. Those will be very much welcome. And I would like to thank Professor Ricardo Vencio for the opportunity. I learned a lot. I had never done a video lecture before, and that was really interesting. I hope my next videos will be better, and thanks again for watching this. And again, feel free to comment and make suggestions and everything. Thank you.